Good evening, everyone, once again, and welcome to the final session for the course Deep Learning for Computer Vision, conducted by Professor Vineet. In today's session, we will kind of review all the questions which we've discussed from week 1 to week 12 throughout the entire course in the live sessions. So, I won't discuss all the questions, but some questions from each week so that you can get a hold of what type of questions you can expect, and like it's a practice for you. So feel free to ask me any questions related to any of the problems which we'll solve today or any other things. You can either unmute since the class strength is less, or you can also post your questions in the chat. So maybe I'll just quickly discuss what are all the things we professor has covered throughout the weeks. So in week 1, professor has given an introduction about images, convolution, correlation operations, even histograms and all. And then in week 2, he's talked about SIFT algorithms and other traditional computer vision algorithms. Whereas in week 3, professor started discussing about the deep learning basics like multi-layer perceptron, and he talked about different optimization techniques like gradient descent, batch gradient descent, and other regularization techniques or dropout techniques, etc. Then in week 4, we discussed about convolution neural networks and how it works and how you can apply it, create a big CNN network to do simple taskless image classification and everything. And then week 5, I think we discussed about object detection, image segmentation, UNet architecture. Then after that, we discussed about recurrent neural networks and sequence modeling, especially which will be helpful for videos and all. And then we went a little bit into attention in itself, like how attention was used, and then how it led to something called a self attention, and then from self attention how people created the transformers. And then we discuss about how transformers initially was limited to text, but then people applied a variant of transformers called vision transformers, VITs, which was able to process images in a similar format. And then you saw about how there are different variants of VITs like DETR models, and even I think, yeah, different forms of VIT models which we have seen. And then after that, we've discussed about generative models like GANs and VAs. And then we also discussed about the latest generative models like diffusion models. And then we go into a bit about the self-supervised techniques, and also models like SimCLR, and also latest techniques like vision language models like CLIP and BLIP and BLIP2. And finally end the session with more latest multimodal LLMs like Lava, Gemini, GPT-4V, and etc. So most of the questions today, it will be related to these things. So let's just start it with the first question. So which of the following you think is the valid image coloring formats? Just pick the correct options and you can post your answers in the chat. There are multiple correct answers. Okay, let's discuss. The correct answers are A, B, C, and D. So, except for the last one, RBX, all the other are valid image coloring formats. Let's look at the answers itself. So, RGB, I think everyone knows, red, green, blue. So, that is standard. Then there is something called as RGBA, which is stands for red, green, blue, and alpha. So alpha is an additional channel that represents transparency. So that is another format which you use in certain use cases. So RGBA is a valid image format. Then you also get CMYK, which stands for cyan, magenta, yellow, and black or key. So this is usually used for printing, because in printing the process itself is different from what you usually see in images. So for printing you have a subtractive color model, whereas you want how much the absorption of light happens rather than the reflection of light. So that is why CMYK is a valid image format. Then you also have the standard hexadecimal, So hexadecimal is usually used to represent RGB in hexadecimal format. For example, the hexadecimal goes from 0 to 15. Like you have your decimal format, which goes from 0 to 9. Hexadecimal goes from 0 to 15. So you represent white in hexadecimal as this particular representation, hashtag FFFFF. Similarly, black you represent it as number 00000. So all A, B, C, D are the valid options in this. So I hope this is clear. In any At any point, if you have any questions, just stop me. I'll just keep moving forward. Okay. Now let's go to the second question. So the second question says, let A and B be two matrices of these particular sizes. A is 2n cross 2n, B is 2p cross 2p. And then we are saying, suppose A is a skew symmetric matrix. You should remember the property of skew symmetric matrix. For now, I'll tell you it is A transpose is equal to minus A. And B is a symmetric matrix, which is B transpose is equals to B. And we're saying let C be B convolved on A. Then what is the sum of all the elements of C? So just post your answers out of all these four options. Okay, let's discuss the answer in the interest of time. So let's see what the process to solve such questions are. So the correct answer is 0, option C. But let's look at what how you can solve this problem. So first, what was the given thing? A is a skew symmetric matrix. So like I said, skew symmetric means A transpose is equals to minus A. And also another property of skew symmetric matrices, the sum of all the elements of A are 0. Why? Because A transpose is equal to minus A. It means that all the diagonal elements are 0 and every other element in A should be equal to the transpose of the negative of its element. So that is why, like I said, Aij is equals to minus Aji, and all the diagonal elements are equal to 0. So sum of all the elements in A are 0. Now, if all the elements are A are 0, then what is convolution? Convolution is nothing but weighted product of the elements of A, right? So if sum of all the elements of A is 0, any weighted sum, regardless of whatever the values in B are, it will also be 0. So that is why the convolution C matrix, if you sum up all the elements of C, it will also be 0. So hence the correct option in these are C, which is 0. Okay. Any doubts or anything that is unclear in the explanation? Okay, great. Let's move ahead then. So this is a simple question. Given the following kernel K, which is a 3 cross 3 kernel, we need the question is the following kernel separable? Also, what are its singular values? Maybe for now, you can just tell me, do you think if the following kernel is separable or not? So separability comes is if you can break this particular kernel into two simple vectors, which can be then multiplied together like u into v transpose, and you'll get back the same kernel. Okay. Any guesses at all? Like, what do you think? Is the kernel separable? Is just yes or no? Any guesses? What do you think? Okay, let's see how to solve such type of problems. So the answer is no, the kernel is not separable. So let's look into how the separability can even be calculated. So let's say we have the kernel matrix K. So there is a theorem in matrix theory which says that SVD decomposition theory, basically it says that any matrix K can be decomposed into the following three elements: U matrix, sigma matrix, V transpose matrix, and which these are matrices, but if you break them in terms of the vectors, it is nothing but summation of sigma I ui vi transpose. So don't worry about what these ui vi is, that is not needed. What is needed over here is you need to know whether this case can be written in terms of only one particular sigma I ui vi. It means that in this entire summation expression, only one term should be non-zero, all the other terms should be zero. When is that possible? That is only possible if only one sigma I is non-zero, remaining all sigma i's are zero. Now, what are these sigmas? These sigmas are singular values, and singular values has a close relationship with the linear dependency of of the columns of a matrix. So all you have to do is find out whether the columns in these matrix are linearly independent or dependent, and find out what is the rank of this matrix. If the rank sorry if the rank is 1, then it means that K can be only represented with only one non-zero singular value, and remaining all singular values are 0, and then K can be expressed as a separable matrix. Whereas if the rank is not 1, greater than 1, there will be more than one non-zero sigma i's, then K cannot be expressed. In this particular case, there are 3 sigma i's, the rank is 3. That is why K is not separable. So hence K is not separable. Any doubts? Anything that is unclear in this solution? Okay, great. Now let's move on to the next question. So this is a very simple question based upon the linear filter concepts. So let's say I have a simple image thresholding concept. Like you see the image on the left of Mona Lisa. If you do a certain type of thresholding, if you apply a certain thresholding function defined as above, you will get the output as the right side. Now, what does this function itself says? Very simple function. It says that if the intensity value of any pixel or the pixel value is greater than 0 100, then you just make it 255. Whereas if the pixel value is less than 100, it is 0. Now the question is, can this simple image thresholding function be implemented as a linear filter or not? You need to remember the property of linear filter. The linear filter property is basically uh, composition property, like a plus b of the function is equals to function of a plus function of b. That should be satisfied for a linear filter. So just use that property and tell me whether this particular function can be linear or not. Yes. Sorry, I think someone answered as yes. No, so actually G operation is non-linear. Let's look at why it is non-linear. So like I said, two image like a function can be linear if g of a plus b is equals to g of a plus g of b. Right now, let's take a simple example and check whether this relation itself is being satisfied or not. Now let's take two locations. A of m comma n is 90, and b of b comma n is 20. These are the two images. Now let's apply g of am at this particular location becomes 0 because 90 is less than 100. Similarly, g of bm becomes 0 because again 20 is less than 100. Now when you do a plus b at that particular pixel location m comma n, both a and b values 90 plus 20 is 110. Now g of a plus b, which is 110, is 255. So 255 is not equals to 0. That is why this operation is non-linear. So just take any simple example like this and you can easily quickly understand whether a particular function can be implemented as a linear filter or not. All you need to remember is this linearity condition. Okay. Let's move on to the next question. Let's go to the convolution operation itself. We remember, if you remember, professor has discussed of three different types of operations: local operations, global operations, and point operations that can be done on an image. So let's see. These are the five different operations. Please identify which of the operations are local, global, and point. You can just write A is what, whether local or global or point. Similarly, B, C, D. What are the operations? Yeah, I think wherein you're more or less correct, one option is wrong in yours. Just make sure you check them again properly. Okay, I'll just discuss because we have a lot of questions. Let's just move ahead. So the answers are local, point, global, point, global. Let's go back to the options. Convolution is a local operation. It's a kernel 3 cross 3, so you're looking at local. That is, I think, clear. Cross correlation, ideally it would have been local, but since we are saying 1 cross 1, it is a a point operation. Fourier transform is done on the entire image, so it's a global operation. So Fourier transform is not local, it is a global operation. It's done on the entire image. Sure product is nothing but element wise multiplication, so it is again a point operation. Flip the image is again global operation because you have to flip the entire image. You need to know the entire image to flip the image itself upside down. So the answers are these: local point, global point, and global. Okay, I hope this is clear. Yeah, let's move ahead. Now let's go to the perceptron algorithm itself. A simple perceptron f is given in this particular question, and f is mapping from R4 to R. So your input vector is these four values: 0.5, minus 0.7, 0.9, 0.3. You're also having a corresponding weight vector for this input with these values. All you have to do is compute the derivative of tan h of z, where z is nothing but the linear combination of the weights vector w and the input vector x. Ignore the bias term. So remember that you'll have to know what is the derivative of this activation function tan h. So there are certain common activation functions like ReLU, tan h, sigmoid, for which you will have to know the derivative of these three functions. Let's look at the answer itself. So first thing is what is Z? Like we defined, Z is nothing but a linear combination of the weights and the input X. So Z is nothing but W dot X, which these are the vectors basically. So it's nothing 0 point minus 0.87. You just have to multiply element wise 0.6, 0.5, element wise multiplication, then sum all those terms. That's nothing but the linear combination. The value of Z is minus 0.87. Now we know that what is the formula for tan h of z? E to the power z minus of e to the power minus z divided by e to the power z plus e to the power of minus z. Now we have to do the derivative of this with respect to z. That is what you will get at the bottom. When you complete all the derivations, the derivative of tan h of z is 1 minus tan h square of z. Now you have to put z is equals to minus 0.87 and just solve for this 1 minus tan h square of z. Approximately you'll get the answer close to 0.5086. Don't worry, numericals we usually have some buffer. So if you don't get exactly to the dot decimal, it's not a problem. Usually there'll be some buffer. But the process, I hope it's clear. This is how you need to solve this particular type of problem to identify the derivatives of a particular activation function at a particular point of z. Okay, let's move ahead then. Okay, now let's look into the dropout technique itself. So there are four statements given related to the dropout technique. Identify which of the statement is true and post your answers in the chat. Uh, Ashwini, the answer is not C. No, it's not D also, Viren. Just think about dropout. What does dropout do? It just drops randomly the network. Uh, Shruti, the answer is not A. So actual answer is B. So let's go ahead uh, and discuss why it is B. Okay, firstly, what is dropout? Dropout basically idea is to drop randomly some connections in the neural network. And why do we typically do such type of things? Is to avoid overfitting. So when you have your model to be very big and your data or the task is very simple, model usually overfits on such type of in such type of settings. So when you randomly drop the networks, now we are enforcing the model to avoid this by-hearting or overfitting and actually learn the patterns. So option A immediately is wrong because it says dropout during training causes the network to overfit. It's opposite. Dropout reduces overfitting. So A is false. Now let's go to C first. C says dropout during training leads to smaller final model size as some connections are permanently removed. So this is wrong because in dropout we just temporarily randomly drop connections, but it's not like that is permanently removed. Like for in one iteration, you drop connections 2 and 3. In the next iteration, you drop some other connections 4 and 5. But again, you retrieve 2 and 3 which you dropped in the previous iteration. So dropout never reduces the model size. It just temporarily removes some connections. Nothing about dropout is permanent. So option C is false. Option D says final output during training when the dropout is applied is multiplied by the dropout rate to maintain the expected output when dropout is not applied. This is false. There's no multiplication of anything that is happening with dropout. You just randomly drop and expect the model to learn patterns instead of overfitting. You don't multiply the output with any scale dropout rate or anything. Nothing of that sort is done during dropout. So the correct answer is B. What does B say? During training with dropout, the network adjusts the activation levels so that the outputs remain consistent when dropout is not applied during inference. That is exactly what we want. So uh, if with the dropout, if the input image is actually a cat, if with the entire model the model is predicting as cat, which is correct, but if you drop out certain layers, the model should still predict it as cat. It should not immediately predict it as dog. That is what this statement means. So option B is true. Okay, I hope all these options are clear. Correct option is B. Let's move to the next question. So this question again, there are four statements given in relation to the techniques like L1 regularization, L2 regularization, and batch normalization. Identify which are the true statements out of these four. Wherein C is not right. Just look at exactly what does C say. Read every part of the statement C. One part of it is wrong. Yeah. Yeah, I think B is correct answer. The actual answers are B and D both. So let's look at what the options say one by one. First thing, I think it's very clear. There is no constraint at all that batch normalization cannot be applied with L1 or L2. It can be applied in conjunction with L1 and L2. So option A is false. Option B says L1 regularization can lead to sparse weight matrices, which means many of the weights are zero. This is true. Why? Let's look at this diagram. So this is how a typical L1 regularization makes the weights look like. It creates, normalizes the weights to in the shape of a rhombus or a diamond shape. And now this loss curve, the closest it can come and touch this weights is at the edges. And at the edges, one of the other weights will become zero. So that is why most of the weights are tend to being zero whenever you apply this L1 regularization. So option B is true. Option C, it's a bit tricky because it says batch normalization normalizes the inputs of each layer by subtracting the batch mean and dividing by batch standard deviation. This part is completely correct. The part which is wrong is it slows down the training. That is wrong. In fact, batch normalization speeds up the entire training process because it normalizes the value intermediate activation values, which can speed up the process of training. So option C is wrong because it doesn't slow down the training process. Then option D says when using batch normalization, it is necessary to disable it during inference phase. This is again true. That is why you do model.eval. So during when you do model.eval, when you write that in code, right, it immediately tells PyTorch that now the inference phase has started, and it disables all components like batch normalization, dropout. All of these techniques should not be applied during inference. These are only training time techniques. So option D is true. Correct answers are B and D. So let's move ahead. Okay, now this is a question based on RMS prop algorithm, gradient descent algorithm. No, the question is find the new value of the parameter theta at basically theta of t plus 1, given that the old value of theta t is equals to 1.8, aggregated gradient delta theta t is 0.6, gradient accumulation rt minus 1 is 0.4, learning rate alpha is 0.1, decay rate rho is 0.6, and a small constant of 10 to the power minus 9. You can just round off the decimals to three places. Remember what is the update equation for RMS prop algorithm, and you can just apply all these values and get the answer. I think I'll just discuss this one because you all need to remember the formula itself. So make sure you have to remember the update formulas for RMS prop. So for RMS prop, the update parameter is basically theta t plus 1 is equals to theta t minus of alpha divided by under root rt plus delta into delta of theta t. Here rt is nothing but the accumulated gradient which is coming from the top equation. Rt is equals to rho of rt minus 1 plus 1 minus rho of delta theta t whole square. So if you know these formula, it's just directly you just have to put substitute the values which are given in the questions, and it's just direct calculation. So make sure you remember RMS prop equations and also the other gradient algorithm equations. That is very helpful. Okay, now let's move on to another question related to the gradient descent itself. So here you have five statements related to the different gradient descent methods that can be used to train the neural network. Identify which are all the true statements in these five. Uh, your option 4 is not right, and option 3 is also not right, Savita. Okay, let's discuss itself the options. So the correct answers are 1, 2, and 5. 3 and 4 are actually wrong. So let's go. Let's first discuss. Okay, maybe let's look at the figure itself. So what does batch gradient descent even do? Batch gradient descent basically updates the model after it looks at the entire data set in its forward pass. So once the model looks at the entire data set, then only it will update. It takes one update step. One update step in this, you can think of it as one arrow mark. So as you can see, because you're looking at the entire data set, your updates are very stable because that is the true gradient, right? So that's why you take a very straight path towards the local minimum. Now in mini batch, we say, okay, because sometimes the data sets are very huge, you can't load the entire data set onto your GPU RAM. So what is the alternative? You split your data set into batches. That is what this mini batch says. You have like 32 batch size, 32 batch size or 64 batch size, whatever. So now when you update, right, after every step, the gradient might not be the true gradient. True gradient will actually look like a straight path. But now we are approximating based on the 32, 64 values. So that is why the path will be a bit wobbly towards the local minimum because these are approximate gradients. Whereas in stochastic gradients is the extreme version of mini batch where the batch size is just one. That is why the variance is even high, like, completely wobbly. So that is why it takes much longer time because the path itself, it goes up and down, up and down, up and down till it reaches the local minimum. That is why this convergence rate of SGD is very less. Now let's look at the options. First option says batch gradient descent can lead to memory inefficiency when dealing with very large data sets. This is true. Like I just said, batch data gradient descent considers the entire batch. Now, if the data set is very high, then it means that you can't load all of that into your GPU RAM because GPU RAM is limited. Today, the best of the best GPUs give you like 48 GB RAM, 96 GB, not beyond that. Those are also very costly GPUs. So that is why first option is true. Second says SGD often leads to a noisy path towards convergence. That is true because we just saw how highly variant it is, but can also help model escape local minimum. That is also true because since you're wobbly enough, like very noisy, it can easily escape the local minima and go probably towards more better minimas. But that being said, it can also escape the global minima because it's just noisy. So option 2 is true. Option 3 says many batch gradient descent is always faster. So the problem over here is the term always faster. It's not always faster. What if the data set is small? It can fit on the GPU RAM. Then mini batch gradient descent is the same as batch gradient descent. So there is no term of always faster over here. So that is why this answer is false. Option 4 says SGD guarantees faster convergence to global minima. False again because, like I said, it's very wobbly or very noisy. So it always, since it's very noisy, it keeps on deviating a lot from its actual trajectory towards the local minima. It just keeps going up and down, up and down. So option 4 is false. Option 5 says using smaller mini batch in size in mini batch gradient descent generally increases the variance of the parameter updates. Again, true because, like I said, mini batch size, if it's one, it is gradient stochastic gradient descent like this. So the if it's a bit like 32 64, it look like this, but the closer you get to one, it will become this. So that's all exactly what option 5 says. So option 5 is also true. So the correct answer is 1, 2, and 5. Okay, let's move ahead then to the next question. So you all remember the mix-up algorithm, right? Mix-up augmentation. What it does is that if you have two training samples, like here we have x1, y1, x2, y2, you have a certain type of convex addition, we say, or just you can simply call it weighted addition between these two x1s, x2, and y1s and y2, and the mix-up parameter lambda is 0.3. So calculate what is the mix-up augmented sample. So it's very simple addition, weighted addition, and nothing else. Just think about it and let me know what is the mix-up augmented sample. Okay, let's discuss the solution. So the correct answer x mix and y mix is as follows: 0.6261, 0.39, y mix is 0.3, 0.7. The formula is very simple. Your x mix is nothing but lambda into x1 plus 1 minus lambda into x2. You have both the vectors, you just multiply them with lambda and 1 minus lambda and just add them up. Similarly, y mix formula is the same, lambda into y1 plus 1 minus lambda into y2. Just simple multiplication and addition, and then you'll get the answers: 0.62, 61, 39, and for y mix 0.3 and 0.7. 0.7. Okay, I think this is straightforward. I'll just move to the next question. Okay, this is an interesting question. Consider the following neural network f of wx, which is of this particular composition: w2 of g of w1 of x. Here g is your activation function, which is tan h, non-linearity. If we use a simple cross entropy loss and if we initialize the weights w1 and w2 to 0, will the network be able to learn or not? That is the question. So think about how the network learns. It's basically the back propagation and updates. It means you need to have non-zero gradients. So are the gradients affected if we initialize the weights w1 and w2 to 0? And if so, will this particular network learn or not? Yeah, that's correct, Viren and Ashwini. They cannot learn. So let's look at the solution itself. So Z1 is W1 of X, A1 is G of Z1. This is the output of after the activation. And since Z1 is nothing but W1 of X, W1 is 0, so tan H of 0 is also 0. Now Z2 is again 0 because W2 is 0 and A1 is also 0. Now let's look at how the back propagation happens. The gradients, right? Partial gradients. So the dou L by dou W2 is nothing but dou L by dou Z2 into dou Z2 by dou W2. Similarly, dou L by dou W1 is this multiplication. And here the gradients will become actually 0. Both the gradients will become 0. And that is why the entire, sorry, that is why none of the weights will get updated and there is no learning that is. So yeah, let's move ahead to the next question. Okay, this is based upon the CNN architecture itself. So here we say CNNs are better than fully connected networks. We all know that, especially for image data. Why do you think is it? Why do you think this is the case? Select the correct answers from these five. Yes, I think it's correct. Ashwini pointed out. Correct answer is both one and two are correct, which is option three. Let's look at it. What does fully connected network? It basically connects every node in the previous layer to every other node in the current layer. So whereas CNNs, that is different. CNN says let's have a small kernel or weight matrix which will slide across the input image. So as immediately the number of parameters that are needed to do the learning is very less. So obviously CNNs are parameter efficient compared to fully connected networks. And also CNNs by design have inductive bias for images. What does this inductive bias mean? CNNs work with the basic idea or methodology that local relation in the images are having some meaning, like the spatial relationships at a local image patch has some meaning. So based on this bias, or we call it inductive bias, CNNs are built. And they're obviously true because in an image, if you look at an object, there are some local relationships for an object in a particular image. Like if you look at the face of a dog, the nose of a dog is at a certain locations compared to the ears, the tongue, and the eyes. There's all locality means have some information which is meaningful. So that is why CNNs are better compared to fully connected networks because they have this bias. So the correct answer is one and let's go ahead to the next question. Here we say that suppose we have an input image of size 3 cross 64 cross 64, the channel's height and width, and the filter size is 3 cross 5 cross 5, and the number of filters used are 3. and the stride is 2 and zero padding is used. What is the size of the output of the filter? Remember, this is very important. This is a very standard question which you usually get in most of the interviews or anything. Calculate the output size of the convolution operation. Output size is not 3. It is answer is actually 3 cross 30 cross 30. So this is the formula for the output size. So it is nothing but your input image or height or width minus the kernel height and height or width plus 2 times the padding divided by stride plus 1 and whole function values taken to the floor of it. So this is the final output size 3 cross 30 cross 30. So just input the values. Here we have W as 64, K is 5, and P is 0, and S is 2, and plus 1. And this is the output which you get. Why this channels 3 you're getting? If you remember, number of output filters that will come output as is the number of filters that are being used. So each 3 cross 5 cross 5 is being convolved with this 3 cross 5 cross 5 patch in this entire image, and like that you have 3 such type of filters of these 3 cross 5 cross 5. Okay. Let's go to the next question. Again, based on CNNs. So usually we have different features that are being learned in CNNs because there's so many layers. Some initial layers are called the shallow layers, that is denoted by S, and the final layers are called the deeper layers, that is closer to the output, right? Those are the deeper layers, D. So given these four options on these S and D, what are the correct ones? Yeah, B is the correct answer. So what does usually a CNN low level features learn? They learn very primitive features like edges, textures, and all those things. As you go deeper and deeper, those primitive features kind of become more complicated or attached to each other and learn more complicated parts like content of the image or different object paths or different curvatures and all those things. So option B is the correct answer. Remaining all they are wrong. S image labels D pixel intensities is wrong. D says no features are captured, that is wrong. A is the opposite of B, so A is also wrong. Okay, let's move ahead. So this is based upon the ResNet architecture. Which of the following statements are true with respect to the ResNet architecture? Okay, let's discuss. So the correct answers are A and B. So what does ResNet architecture even say? Yeah, I think Brian pointed out correct answer is 1 and 2. So what does ResNet architecture even say? It says that you need to have some skip connections or residual connections that will help the gradient flow properly from the deeper layers to the shallower layers. That is the entire idea of ResNet connection. So option A is true because you have some skip connections. Option B is true because these skip connections were invented with the idea to avoid this vanishing gradient problem. Option C says it works only for shallower depth architectures, which is false. ResNet has variants like ResNet 100 layers, 50 layers, 124 layers also, I think. So it has a huge, deeper network. So C is false. Skip connections requires extra parameters. Wrong. Skip connections is literally nothing but just an addition and nothing else. So there is no parameters at all. So option D is wrong. Let's go to next question. Here it's based on inception net. So here inception net, I use this one cross one convolution layers. Identify why out of these four statements do we need this one cross one convolution layers. Yeah. Answers are B and C. So let's look at the answers. I think we have explained here clearly. Uh, Kernels usually with low sizes usually encourage more local than global information. So that is why this is not the reason for one cross one convolutions were incorporated in inception net. And parallel convolution across layers is done over the one cross one convolutions, not sequential convolutions. So that is why options B and C are true, not A and D. Okay, let's move on to the next question. What are the advantages, I would say, of efficient nets? These are the four options. Pick the correct option. Yeah, the correct answer is 1, 2, and 3, as Viren pointed out. So let's look at options one by one. It relies on compound scaling of depth, width, resolution, and architectures. That is true. Entire efficient net is proposed based on something principle called as model scaling, which is basically a relationship between these three parameters: depth, width, and resolution of the particular architecture. A is correct. B says the general principle of model scaling can also be applied to mobile nets ResNet. That is true. In fact, you can make the architectures much more efficient by just applying this rule of model scaling, any architecture. C says it helps design architectures that achieve maximum accuracy under a given budget of resource constraints. Again, one of the motivating factors for coming up with the scaling law. Finally, D says takes long time to train. There is no evidence. In fact, mobile nets are faster to train. So, using these efficient nets, so there's no evidence as such to where that these efficient net models take long time to train. Okay, now let's move on to a bit of the tasks itself: object detection, classification, and semantic segmentation. So there are four tasks: detection, classification, semantic segmentation, and instance segmentation. Identify which are the following correct statements in these four related to these tasks. Yeah, D is correct, but there is also another correct answer in this option. Yes, the correct answers are B and D. So let's look at the options itself. Object detection involves classifying. Okay, let's maybe go by the definitions itself. What does classification say? Classification is basically you given an input image, you have to just simply classify whether that particular image belongs to a particular type of a class, like cat, dog, truck, aeroplane, whatever it is. Object detection says you need to classify each object present in that image and also draw a bounding box across each of these objects. That is what object detection task is. Next comes the segmentation. Semantic segmentation basically identifies and classifies each pixel into a particular fixed set of categories, like whether this particular pixel falls in class A, B, or C. Instance segmentation not only segments and classifies each pixels, but also keeps track of each instance of the picture object. Like for example, if there are three chairs back to back, semantic segmentation will give the same color to all the three chairs, whereas instance segmentation identifies there are three different chairs and gives a different color to each of this chair. So that is the difference between instance segmentation and semantic segmentation. So based on the definitions, the correct answer is B and D. Okay, let's move ahead. So YOLO is one of the popular object detectors, and there are four versions which have been discussed. I mean, currently there are 10 versions, but the question is only based on the first four versions. So based on the different architecture and strategies that were proposed in each of these four versions, identify which are the true statements. Okay, let's discuss. So the correct answers are A and D. B and C is the wrong options. Let's look at the options itself. YOLO V1 loss function, being primarily focused on regression of bounding box coordinates, heavily penalizes small localization errors, but it struggles with detecting smaller objects due to the grid cell constraints. This is exactly true. This is what the limitation was actually for YOLO V1. So option A is true. And next, option 2 says YOLO V2 introduces the use of anchor boxes and multi-scale training strategy, which is wrong. YOLO V2 actually doesn't use any multi-scale training, which improves detection. Multi-scale training strategy is true. It actually doesn't use the same loss function as YOLO V1. YOLO V2 actually changes the loss function from YOLO V1. So option B is false because it says it uses the same loss function as YOLO V1. C option says YOLO V3 improves upon YOLO V2 by using a multi-scale feature pyramid and a binary cross entropy loss for classification, which reduces the false positive rate in dense object. However, YOLO V3 abandons anchor boxes. This is false. Anchor boxes are still used in today's YOLO methods also, YOLO V9, 10. So anchor boxes is still there. So option C is wrong. Option D says YOLO V4 incorporates innovations such as CSP darknet, mesh activations, mosaic augmentations, and the loss function also balances classification, classes loss, location loss, with the addition of CIOU loss. All of these are actually the main contributions of YOLO V4. So option D is also true. So this is a bit of a lengthy option. So you need to know have an idea of these architectures to answer these questions. So correct answers are A and D. Let's move on. Okay, now this is a very simple question which most likely you might encounter also, which is called the IOU, intersection over union. So you're given two bounding boxes, top left corner, bottom right corner for each of the bounding boxes. So you have to just calculate the IOU. Remember what is IOU? Intersection over union between any two bounding boxes. So yeah, use that formula of IOU and then let me know what is the IOU value. Okay, let's solve this question. So maybe I'll just quickly draw it out. Maybe it'll be easy. So in images, this is how we usually have axis travel on from left to right, and y-axis is basically travels from top to bottom, all positive values. So here, first value, what do we have? We have uh, between. Sorry, go back. So the top left is 2 comma 4 and bottom right is 8 comma 10. So let's say this is 2 and this is 4. So 2 comma 4 is somewhere here. 8 comma 10 will be somewhere here. So this is my box A. Now what is the box B coordinates? Box B says 5 comma 6 and 12 comma 4. Okay. 5 comma 6, which will be somewhere here, and 12 comma 4. Sorry. Yeah, 12 comma 14. Yeah, sorry, 12 comma 14, which will be somewhere over here. So this will be my box B, and we need to calculate this part, intersection over union. Union is the green color. So now these are all rectangles, right? So you can calculate quickly the area of any rectangle. So intersection of union, intersection area is nothing but this small rectangle, the common points, which you can quickly calculate, which is nothing but 8 minus 5 into 10 minus 6, which is 12, which is width into height, area of a rectangle. Similarly, union area you can calculate with this formula, area of A plus area of B minus intersection area. I think this is a very standard formula. I'll explain again why. What is union? Union is this entire what do you say, two rectangles square, the entire area of these two rectangles, right? So if you calculate area of A, it is this blue box, area of yellow, which is this yellow box, area of B, and intersection is now being calculated twice. So that is why we subtract once the intersection area. So the final answer for union is 80. So 12 divided by 80, answer is 0.15. So I hope you're able to follow this. So let me know if there are any questions in this. I think very straightforward. You Yeah. Okay, then let's move ahead. So this is based on the faster RCNN and fast RCNN object detector. So it's another type of another family of object detectors, which is called the two-stage object detection. So identify which are all the true statements with respect to these two models. Okay, let's discuss the answers. So the correct answer is just B. The remaining all are false. Let's go the options one by one. What does first option say? Fast RCNN improves upon RCNN by integrating the region proposal step into the network. This is wrong. In fact, fast RCNN doesn't do that. It still uses selective search algorithm. It is faster RCNN, the option B, which actually uses the region proposal network with the in the complete architecture. So A is wrong, B is true. Next option C says in faster RCNN, RPN generates object proposals directly from raw input images Again, false. In fact, RPN, the input to region proposal network, is after the convolution is done on the input. Then you get some features of the convolution. Those features are being sent as an input to RPN network. So RPN network doesn't directly take raw images; it takes the features of the convolution. Option D says both fast RCNN and faster RCN uses a sliding window approach to generate region proposals, which is again wrong because just like I said, fast RCNN uses selective search, faster RCNN uses region proposal network. So option D is wrong. Okay, let's go to the next question. So this is based on the segmentation model, UNet model. So identify which are all the correct statements with respect to the UNet. Yeah, sorry about that. I think yeah, sorry about that error. So let's go look at the correct options for this. The correct option is B. So what does unit model even say? Unit model is basically special, or it worked out in a very nice way because they had skip connections between the encoder and decoder. So any segmentation model for that reason needs an encoder and decoder. Encoder takes the input, encodes into a smaller dimension, and now that bottleneck layer of the small dimension is taken as an input to the decoder, and then the decoder upsamples until you get the same shape as the input. This is what a typical encoder decoder model looks like. Obviously, in unit, we use CNN ResNet 50, ResNet 50 or 101 as the backbone. The advantage was they were having some skip connections between layers of the encoder and the layers of the decoder. Now, that was advantageous because it helps in preserving some spatial relationships which were captured during the downsampling in the encoder, and it gave that context to the decoder when it was upsampling. So that is the entire advantage of unit model. Now that being said, let's look at the options. The unit model is characterized by its use of fully connected layer at the end of the network, which ensures that the entire image is classified as a single label. False. Like I said, unit is a segmentation. What does segmentation do? It identifies each pixel, classifies each pixel, not the entire image. Option B says unit uses encoder decoder structure where encoder downsamples input image and decoder upsamples to produce pixel-wise segmentation maps with skip connections that combine high resolution features from encoder with upsampled output. This is exactly what I explained right now. So option B is true. Option C says unit model solely relies on convolution layers without any pooling operations, making it highly suitable for tasks. Wrong. Unit has pooling operations. So option C is wrong. Option D says in the unit architecture, skip connections are used to merge the output of the decoder with the input image. Again, wrong. It is between the encoder layers and the decoder layers, nothing to do with the input image. So, hence, the correct option is B. Now, let's move. So it's simple question on RNN. So there are two sets, set A and set B. Set A talks about the type or the setting of the RNN task itself, and set B talks about the specific example of that particular setting. Just do a quick matching between set A and set B.
Many to one sentiment classification, many to many is machine translation, and one to many music generation.
Yes, that is true. One to many music generation, many to one sentiment classification, and many to many machine translation. So I'll just quickly go over by music generation. You just take one particular input and you generate the entire music. That's why one to many. Many to one sentiment, like you're given an entire text or a big paragraph, and you need to classify whether it's a positive or a negative statement. That is why many is like the huge text. One is basically the label, positive or negative. Many to many is translation because your input is also a different language and your output is also a different language. Okay, now let's go to another question. What are the problems with traditional RNNs? These are the five options. Pick the correct option which you think is the problem with traditional RNNs. Traditional RNNs with context to your latest transformers and all.
So all the above.
Yeah, that is true. Like Pavani has suggested, all the above is correct. So I think vanishing gradients and all, everyone is aware in RNN has a problem. Even dealing with long-term dependencies, after a point, RNNs or LSTMs for that reasons drop this capability. Like they have a reduced capability to deal with long sequence. That's why attention mechanisms work. Even processing the data sequentially, that's a problem, especially in terms of memory constraints, whereas transformers do it parallelly of processing of data. So actual option is all of the above. Let's go to the next question. It's based on LSTMs and GRUs. So there are different attributes to each of these network, like number of gates, memory cell, gating mechanism, complexity. Identify the correct statements in each of these attribute between LSTM and GRUs.
In one, LSTMs have 3 gates, while GRU has 2 gates.
Yes, B.
Yeah, yeah. Please do it for all, and maybe you can post it in the chat.
And 3 is B.
Okay. Okay. Let me discuss the answers itself. First option, actually, all of them are B. Let's look at the
All are
answers.
yes.
Yeah, let's look at the answers. Number of gates, this is standard practice. I think this is definition of LSTM. LSTM has 3 gates, GRU has just 2 gates. Then memory cell. Memory cell talks about LSTM usually has a separate memory cell, whereas GRU in a way kind of has a combined memory with the hidden state. That's why lesser gate we have in GRU. So that is why LSTM has a separate memory cell, while GRU is combined memory into hidden state. Gating mechanism, LSTM has 3 gates.
Sorry to interrupt. Is there any relation of memory cell with the gates?
So memory cell,
I think in GRU the input gate and
for gate and output gate.
is combined.
Wait, sorry, in GRU? GRU has two gates: update gate and reset gate.
Yeah.
Yeah.
My question is this gating mechanism has any relationship with memory cell?
No,
I am asking this question because if we drop the memory cell in GRU, then number of gate reduce. Is this the reason?
no. Memory, it's not directly related. Inherently, like implicitly, it's related, because here, if you're separately having a memory cell as such, whereas in GRU you combine that memory implicitly with the hidden state, like an extra parameter. It has not a direct correlation, but you can think of it dealing with like a separate gates itself. But it's not direct correlation. You can't think of it as a direct correlation. So here option 3 says LSTM uses input, forget and output gates. Those are the three gates. That's true. Well, GRU uses just two gates. Which are the two gates? Update gate and a reset gate. And then complexity wise, GRU are less computationally expensive, again because fewer gates. They're just two gates than LSTMs, because LSTMs have three gates. So the correct options in all these options are option B. Okay, now let's look at a question. Which of the matrices are responsible for vanishing and exploding gradients in RNN? So these are the two equations which you have in RNNs, hidden state update and output YT, which depend upon the other terms. Sigma is the activations, W is the weights, XT is the input, U is another weight parameter which is multiplied with the previous hidden state value HT minus 1. B are the bias terms. So which out of all these matrices is responsible for the vanishing or exploding gradient? Think about what causes the exploding gradient or vanishing gradient and identify.
First one,
Which is first one?
HT is equal to sigma.
No, HT is not dependent. No, HT is not.
Because I'm saying this because while we are exploding or vanishing gradient calculated by back propagation, and if number of layers in HT increases, that's why vanishing gradient, the probability of vanishing gradient increases. That's why I'm saying
No, it's not the probability of increasing. It is why it is even increasing. That is the question. Why? So what? So basically, the gradients should travel back, right? So what?
yes,
When the gradients are traveling back, something is multiplied with those gradients that is making it smaller or bigger.
yes,
What is that value that is being multiplied with that gradient? H of t is not getting multiplied with any of the gradients. So it's actually u of h when you're calculating. Yeah, UH. It's actually UH. UH matrix is getting multiplied over and over with the gradient values, and because of the property of UH, it can either shrink the gradients or it can either explode the gradients. That is why the gradient problem happens. So the correct answer is UH. Now, similar to that particular concept itself, here, what if the UH is having an eigenvalue greater than 1? What are the potential issues that might arise during the training process? Correct. Select, pick the correct options.
B.
Sorry.
Second, 2.
Yes, 2. Exploding gradient is the correct answer. So why is that the case? What are eigenvalues usually do? So if you don't understand the concept exactly of eigenvalues also, what you can think about eigenvalues is when eigenvalue of a matrix determine how it transforms a vector that is being multiplied. So if you have a matrix like UH and you have a vector X, and if this matrix UH has eigenvalues greater than 1, then it increases the length of this vector after multiplying with this matrix UH. Whereas if the eigenvalues are less than 1, when you multiply a vector with such matrix, it reduces the magnitude or the length of these input vectors X. So same idea here, like I said, UH multiplies with the gradient. So if you're having eigenvalues greater than 1, then the gradients are keep on increasing and increasing and they explode. So that is why option 2 is correct.
Similar to ReLU.
Similar to, sorry, what?
ReSU activation function.
Sorry, activation function is, why did activation come here?
Similar to ReSU, because ReSU preserve the same value if the value is positive or greater than 1. So the exploding gradient problem exists with ReSU activation. That's why I'm
No,
saying.
no, 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 no. Not necessarily. Gradient exploding and vanishing gradients is just dependent on the gradient value. It doesn't have to do with any of the activation. If the gradients become smaller and smaller, it can cause because of any activation. It's not necessary that only ReLU causes it.
Yeah, I am saying that the activation related to ReSU are creating the problem of exploding gradient, because 10H or sigmoid are existing between 0 and 1 or -1 to 1. That's why they can't.
No, you're talking about the output of the activation. No, no,
Yeah,
you talk. That is not the causing the gradients. Gradients are the back propagation. It's not the forward propagation.
talking about back propagation, even you have to back propagate through the activation function also. You have to differentiate the activation function also.
Yeah, yeah, but
Propagation.
no, but
That's
when you
why.
say no, no, but once you get that gradient, if I multiply with this vector of UH, let's say UH itself, UH has no activation, right?
Okay, okay.
Yeah, UH has no activation. Imagine whatever value you get from behind after activation, after it's going through the activation. If I multiply with just UH constantly, it keeps on increasing. So you still explode the value or vanish the gradients. So it's not necessarily that they have a correlation in that way. Okay. Now let's go to a simple question based upon the autoencoder. So given an input dataset X, can the encoder of a denoising autoencoder learn a many to one mapping from X to X? It's a simple yes or no question.
I think yes.
Yeah, so the correct answer is yes. Why is that the case? What is many to one mapping? If you have multiple inputs and you want to map it to one particular output, that is what many to one says. So
Yeah.
denoising autoencoder, usually the input X, we add some type of noise to the input X before sending it as an input to this encoder. So since we are adding randomly the noise could be of any randomness, right? So multiple inputs will map to the same output, which is the original image itself, which is X. So that is why we have many to one map. Okay. Let's move ahead to vision transformers. So these are the following true statements about the transformers, and pick the which of the following two are the true statements out of these four in respect to the transformers.
Two and four. Okay.
No, two and four not correct. So the correct answer is just option C. Third option. Let's look at all the options one by one. Firstly, it says that vision transformers do not require positional encoding as they are not temporal data, which is false, because here,
Yes.
po- yeah, here the positions is basically giving the patches some meaning, like what position that patch was placed in the entire image. So that is why positional encoding is needed. Input second option says input data is parallelly passed to all stacked encoders, which is false. In fact, input data is passed to the first encoder, which is then output of that encoder is passed to the second encoder, and so on. It is not parallelly passed to all the encoders input data. So option two is wrong. Option three says, yeah,
Yeah.
can you please mute? Okay, you have a question.
Yeah, I have a question.
Yeah.
There are four important part of encoder, decoder, sorry, transformer, sorry, vision transformer. One, the encoder decoder architecture. Second is the positional
No,
encoding.
this is just a transformer in just a transformer, not a vision transformer. Option 2.
Okay, 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 that's fine.
Yeah. Option 3 says input data is parallelly passed to all the stacked decoders from the last stacked encoder. This is exactly what the architecture of a transformer says. You first pass your input data, send it to all the encoders, and from the last encoder, that will be sent as an input to all the decoders. That is what the architecture of transformers is. So option 3 is true. Option 4 says the weight values in each of the QKV matrices of multiple heads of the first encoder of a single transformer are kept exactly the same, but the input of the matrices are kept varied to ensure better generalization. It's the opposite. The weights are different across multiple heads. The input is the same because the weights are what helps in generalizing across different inputs. So weights are actually not kept the same. The input is kept the same. Weights are different values for all the multiple heads of QKV. So option 4 is false. The correct option is only option 3. Okay, let's come to a simple numerical. So here we know that the self-attention mechanism, which we all are aware, is this particular formula: softmax of qk transpose divided by square root of dk, all multiplied by the vector v or the matrix v. And so here we assume that q and k both have dimensions dq and dk. Now suppose all the entries in Q are multiplied by a scalar x and all in K are multiplied with a scalar y. So denote with a positive up arrow or a down arrow whether this particular event of x and y, which are values you're seeing on the bottom, these are different x and y's, whether that will cause the softmax probabilities to get closer in uniform distribution, or they shift farther away from the uniform distribution, or if there is no change at all. So you can just let me know out of these 5 different XY combinations, which will cause the softmax probabilities to get closer to uniform, farther away from uniform, or they don't change at all. Remember, it all depends on a simple relation between these scalars that you're multiplying x and y.
I think no change.
There are 5 options, right? For each of them, you have to tell. So each of them are a different x and y. So there is a relation that you have to understand between x and y, and which of them will give no change, which of them will give more closer to uniform, which of them are farther away from uniform. Okay, let me quickly discuss this. So the relation is xy. If it's greater than 1, it is decreasing, like it will be closer to the uh, it will be farther away from the uniform. If xy is equals to 1, it is no change at all. If xy is less than 1, it is closer to the uniform distribution. Why? So let's see. Here you're multiplying qk transpose. If all of q is multiplied with x, you can remove that outside. If all of k is multiplied with y, you can remove y also outside. So now you will have softmax of xy, x into y, and multiplied with this qk transpose divided by square root of dk. Now let's take if xy is small value, less than 1, like some 0.5. So all of these values which were previously there, qk transpose, those all will be multiplied with a value which is less than 1, which will make them closer to each other. So the softmax of the values will come closer to uniform distribution. That is why you see that. Yeah, and whereas if your q x and y values are greater in than 1, then all of the values which were previously there, qk transpose, those will become farther away from each other, and the softmax values will be farther away in uniform distribution than uniform distribution. Whereas if x and y is equals to 1, then there is no change at all. It just cancels each other out. So based on that idea, just take each of these values as x and y. This is x, this is y, and then identify whether it's greater than 1, equal to 1, or less than 1. you will see these answers basically. Okay. Let's move ahead and let's look at another question. So we have positional encoding PI, positional encoding P, which is described in attention is all you need paper. And we say that let Pij denote the entry of ith row and jth column of the positional encoding. Identify the condition when P of I comma 2j is equals to P of m comma 2n. So which of these m and n particular relation in these four will satisfy this equation? P of I comma 2j is equals to P of m comma 2n. So remember the formula. If you know the formula for the positional encoding, then it's pretty straightforward, this question. I think let me just show the formula itself, and I think you can easily understand the solution. So the formula is sine P of I comma 2j sine of I divided by 1000 to the power 2j by d mod. So all you have to do is equate these two equations together. I divided by 1000 to the power 2j by d model equals to m divided by 10,000, sorry, 10,000 to the power 2n divided by d model. If you simplify it further, you'll get this I into 1000 to the power this is equals to m into 10,000 to the power this. So just equate it and you'll find the relationship whichever is satisfying over here. Now let's move to the VIT question. So here we all know that in VIT model, the input image, if you have 224, 224, if you're splitting into patches, each patch of the size 16 cross 16, then now this patch is then projected into a 768 dimensional embedding space. This is what is usually done. Now to project this 16 cross 16 patch into a 768 dimensional embedding space, what is the total number of learnable parameters for this linear projection layer? You can ignore the bias term.
Uh, 14 cross 14 cross 768.
Not it's 16 cross 16, right? It's not 14, it's 16, right? Because the patch size, each of the patch size is 16 cross 16. So you have to flatten it out, which is 16 cross 16, 256. And then since you're projecting 256 into 768, number of parameters needed is 256 into 768. These are all the parameters that you need. Here we are ignoring some bias terms. So it's a very straightforward. I just flatten it out and just multiply the uh, flattened pixel patch and the 768 dimensional projection space. Okay, let's move to the next transformer, Swin transformer. So Swin transformer, as you all know, introduces this concept of shifted window attention. What is the primary advantage of this shifted window attention out of these four options? Okay, let's discuss. The correct answer is option B. Let's go over each option one by one. So firstly, what is shifted window actually was proposed for was, so basically in Swin transformer, each window had a multiple patches inside it, and inside that window, patches were able to attend to each other. But from window to another window, beside windows, there was no communication or information exchange at all. So to overcome this limitation, shifted window concept came. So now with that idea, let's look at the options. First option says it enables each window to attend to every other window across the entire image. This is wrong. It's not attending to every other window. Like I said, each patch inside that local window will attend to every other patch inside that window, but there's no attention that is happening across windows. That is false. Second, cross window information exchange happens, yes, by alternating between regular and shifted windows across layers. So this is why shifted window concept came. Why this is advantage because local and global features interactions without significantly increasing computations. So option B is true. Option C says it increases the window size dynamically at each layer, which is strong. There is no dynamic window size at all concept at all in Swin transformer. Option D again is wrong because it says it eliminates the need for positional encodings, which is false. Shifted window has nothing to do with positional encodings. Positional encodings is to give a sense of where the each patch was present in the original image. So option D is also false. The correct option is option B. Okay, let's move on to another model, DETR model, which is an object detection model that uses VIT transformers, and it overcomes certain traditional methods like anchor boxes and non-max separation. And it also uses a different loss function called bipartite matching loss. So here, which of the following are best explains the role of this bipartite matching loss in DETR? Like select the one which you think is the best explanation for this particular loss. Okay, the correct, let's discuss the answer. The correct answer is B. Now let's look at each option one by one. First says the bipartite matching loss is used to minimize the distance between the predicted and ground truth bounding box. False. Bipartite matching has nothing to do with minimization of distance at all. So option B is false. Option A is false. Option B says bipartite matching loss ensures a one-to-one correspondence between the predicted and ground truth objects by solving a matching problem between the two sets. That is exactly what is done in this bipartite matching algorithm. You have two sets. One is the predicted set, one is the ground truth set, and you have to solve a matching problem between these two sets. And that's why you don't need any non-max suppression and other techniques that were previously needed for YOLO or faster RCNA. So option B is true. Option C says bipartite matching laws dynamically adjust the number of bounding predicted boxes during training, allowing DETR to predict a variable number of objects. Again, this is lost. There's no dynamic adjustment that is done on the number of predicted boxes. You have a number of predicted boxes that will go into one set and the ground truth in another set, and you just do the matching. Option D says bipartite matching laws enforces strict spatial constraint on object predictions. Again, nothing to do with bipartite matching at all. There is no constraints that bipartite matching laws puts on the space on the spatial constraints on the object predictions. So D is also false. Correct option is just B. Now let's go to the SAM model, which is a segment anything model. SAM model uh, basically can generalize across different input prompts for segmentation models. So which of the following is the true reason for it to generalize across different input prompts? Out of these four options, which option actually helps with this particular architectural choice?
Read.
Sorry?
A.
No. It's actually
A or D? D. A or D?
no, it is C, right? Vision transform with dynamic prompt encoder, because you can give any type of input prompts. You can give points, boxes, masks, and there's a train transformer which takes any type of input prompts and it can encode that and help SAM model to do your segmentation. C is wrong because SAM is entirely trained on millions of label data. It is not unsupervised pre-training. It is, in fact, there's some type of self supervision and label type supervised
Yeah.
fine tuning. So correct option is C. I think there's a question in the chat. Can you please share previous? So, like I said, I'm not the official TA. I'm just a PMRF TA for the live sessions. I don't have previous exam papers. Maybe you can just ask it in the Google forum. Maybe they can help you with that, Pavani. I don't have any previous question papers.
Can you please share the recording of this session?
Yeah, that will be uploaded on YouTube itself.
Okay. From where I can download this, or from where I can watch this video?
All the live sessions have been recorded in the same YouTube playlist link, which is updated in the Google Sheet, right? So you have a Google Sheet link which has been floated on the very first day. So you have all the videos links available in that. I'll post this after the class finishes. As soon as it gets uploaded on YouTube, I'll attach the link in that.
Okay.
Yeah, it takes some time, 2 hours, 3 hours sometimes to upload on YouTube. So after
Okay.
that, it will get uploaded. Yeah, let's go to the next question. So there are 4 different matrices which you see on the screen. Which of the matrices represent a valid transition matrix for a Markov process? So this is based on like a prerequisite for diffusions. So which of these following options matrices are actually a valid transition
A.
matrix? Okay. There's more than one correct, I think. Oh, no, I think there's only one. Oh, no, the two. A and D is the correct. So I'll just explain what is the logic over here. The logic is basically for a matrix to transition matrix to be valid, the rows should sum up to 1. So just sum up all the rows, whichever is giving you 1 for all the rows. That particular matrix is a valid transition matrix. So correct options are A and D. Okay, let's go to another question based on diffusions. So which of the following statements are true based on these 4 different options on diffusions? Correct answer is C. Remaining all are wrong. Let's go one by one. First one says DDPMs explicitly learn the true scoring functions. Wrong. DDPMs never learn true score functions. It is similar to how a score functions work, score function networks work, but it is never learns any true score functions. There are another variant of diffusion models itself which can learn true score functions. Similarly, classifier guided diffusion sampling never learns the true score functions at all. So A and B are false. C is true. You can sample images faster than diffusion models, like your VAEs and GANs. Those are faster than diffusion models. So C is true. D again, there is not a clear distinction as to which model is better than the other. Both of them have their advantages, classifier based and classifier free. So it is not very clear exactly as to which one is better. So usually you won't find such ambiguous options, but if you get something like this, it's not really clear which one is still better, classifier based or classifier free. Both of them have their advantages and disadvantages.
But as per the lecture notes, classifier free model are better than the model having external classifier, because the learning of external classifier is too costly as compared to the classifier free model.
True.
That's why
Yeah. There are definitely advantages. I'm not saying. I'm saying there are advantages of both sides. It's not very concrete. Usually, you won't get such ambiguous options. Don't worry about it. In questions, you'll get very clear options. This, still feel it's a bit ambiguous. But if it's written explicitly in the notes, please follow the notes. If it's explicitly written as classifier free is better, then please follow. But usually, you won't get any ambiguity. Don't worry. But C is definitely true. C, you can easily sample faster in than diffusions of using other techniques. Okay. Yeah. This next question talks about whether during the reversed process, right, in diffusion, the reverse process where you have the neural networks, does the learning remain during the reverse process invariant of the weights of the reverse process time steps? So the question is, does the learning remain invariant of the weights of the reverse process time steps in training a diffusion model? Yes or no? Yeah, the correct answer is no. It doesn't remain invariant. It is highly dependent on the weights because you need to know at what time step you are to identify what the error is that was present in that particular image. So it is not invariant of the reverse process time steps. Okay, yeah, these are all the questions that I wanted to discuss once. I didn't cover just last week's because I thought you just did last week itself, so you can always look at that. But remaining all the weeks, more or less, I've covered. So yeah, any other questions or anything that is not clear that you want to discuss, we can do now. Otherwise, we can end today's session. Okay, great then. I'll just end the recording once.
can you please